Last time we were talking about different impedances at various nodes of BJT oblique MOSFET. Current is here, current today, current or no? No. He's coming or no? Okay. Just for revising, can you tell me, like, Shashank, can you tell me what is the impedance looking into the base? Yeah. This is, by the way, BJT. You have to draw the equivalent smalls in the model. Yeah, Manvendra. R pi. It's very easy. R pi. What is the impedance looking into this emitter? 1 by Gm. By the way, it's an approximated value. However, the original one is 1 by Gm in shunt with R, or in shunt with R pi also. Right? What about this one? So collector is RO. However, if there is no base width modulation, then it's infinite. Okay, if you consider the base width modulation, then this is going to happen. What if it's a MOSFET? If I am looking from the gate side, what is the impedance? Infinite. What about the source? 1 by G. And what about the Z drain? R naught, right? If there is no channel length modulation, then it's infinite. Okay. So there are two properties. We know that if it is voltage controlled current source and current controlled current source, the input impedance and output impedances are as follows. The input impedance is infinite. In this case, output impedance is infinite. This one 0 and this one is infinite, right? So let's agree on one thing. This is an approximation that any resistance you are seeing in ohms, maybe 100 ohm, less than 1 kilo ohm, less than 1 kilo ohm, we are going to consider that one as low impedance or zero impedance. Okay. If it is more than 1 kilo, we are going to call it very high. Okay. So in that case, we also learn that R pi is R pi and 1 by Gm are in similar range, maybe, or maybe R pi might be little bit bigger than 1 by Gm, but it's in similar range, and R0 is much bigger than this one. This is in the range of something like 100-200 ohms, right? And this is in the range of more than kilo ohms, 10 kilo, 20 kilo, depends on technology. So now, can you tell me, if I am looking into this input impedance of this BJT, if the input is applied at base, and if I am looking at the output from collector, this configuration is what? Voltage controlled current source or voltage controlled voltage source, or which one it will be?
Voltage controlled current.
Why voltage controlled current source? Input impedance is no, here is it infinity? It's low, right? At the input side, it's in ohms, 100 or 200 ohms. So input impedance is low. And what about the output impedance? High, right? Because R0 is much higher than these two, and this is considered as high impedance. So this one is current control current source. This is already known to us, but there is one catch. I'll tell you after defining this MOSFET. So tell me, what kind of I'm not drawing this. You have to tell me which kind of device this one is. VCCS. Is there anybody else? Is there anybody who is not agreeing with VCCS? You all agree that this is VCCS, whose input impedance is infinite, output impedance is also infinite, because that's R0, which we are going to call it high because it's in the range of maybe more than 1 kilo ohm, right? So, but there is one catch. All these things are only and only depending from where you are giving the input and from where you are taking the output. It's not. Which one? BJT, current control current source. Hmm? It's current control current source. So we have to follow this one. There are two communities. I told you, like if you are, like if you ask your previous instructor, he will tell you that it's voltage control current source, maybe, right? But that's the wrong thing. It's it's on assumption basis, right? What input you can give, that's the most important part. Voltage or current. Yeah. No, it's very with respect to IV also. That's also. So it's all about the reasoning. You are talking about some abstract thing. Really like for this case, it's because of this voltage, right? Similarly, this is also because of voltage. Output is also voltage in that case. You are taking the output, right? Which is voltage. That's also truth for all the devices, no? Even if it's a diode or anything. But everything is defined by one table, this table. If it is circuits, it's defined by this table. And because of this table, you can apply various voltage or current accordingly. If you remember last time I told you that various circuits, if you are connecting together, or by the way, this particular connection is known as cascade. We are going to study one more. Is there any Bengali here? No. So there is one more cascode. Okay. So that's different than this one. Okay. Because I was studying in Kharagpur and like I used to think that sir is saying cascade, but I am hearing cascode. But that was the wrong thing. Cascade is separate and cascode is also separate. Okay. So there are two different topologies. We are going to study next after this. But cascading means output of one circuit is connected to the input of the next one, right? So when you are doing this, if the output impedance of this one is, let's say, in ohms, and this, right? So if you are seeing 1 volt here, most likely that will be dropped, right? If this is like this is a wire resistance, and if this is input impedance of the next stage, right? If it is infinite, then you can have the exact 1 volt over here, and that's the property of voltage control source. Like you can use the voltage directly without modifying many things, right? So if it is low impedance, then if you want to have the same voltage, you have to convert this quantity to voltage to current, or you have to make sure that the impedances are matching. So that's why we have to follow only this table. Right? So in circuits, we define this way only. And this is like you are in mostly all the books. If it is like all circuit books, I cannot tell you about other books who are working with device, but I also have seen that people are calling BJT as also voltage control current source. Right? But as per this theory, it's current control current source. Okay. We also studied the small signal AC analysis. For quick review, let's draw the small signal model for whatever I am drawing it. Can we draw the small signal model for this one? Somebody can volunteer and draw it here on board. You can try in your notebook first. Draw the small signal AC model, just the model. You have to remember following thing. This is an AC analysis where AC sources will be activated. However, all DC sources will go to 0. This is because we are doing an AC analysis. Get the remark? Any doubt? Yes, Suraj, you got the answer, right? You have not started, right? So you have to replace BJT with the small signal model known to you. I'm not drawing right. I'll wait for you people. Rahul, can you check at the last people if they want some help? If you need help, my TS can help. Vivek, can you help others? Just you have to replace BJT 3-terminal device with an equivalent model. If you need my help, I can also come to your desk. So are they doing or no, Rahul? No, you have to replace this one with small signal model. Shikhar, at the end, yeah. You got it, right? Ashish, can you volunteer and draw? You don't have many jobs. This is very easy, right? It's not so much difficult. So you can verify here. Ashish is drawing the small signal model. You got the answer, Billy? Yes or no? We agree only on the voltage and current sources, not. Okay. What you have drawn, like, it's an advanced version. We have studied in previous course, but I was not asking that one. So, but because of you, I realized that I need to write down one more thing here. This signal is low frequency signal. Still now we are not studying frequency response, so it's a low frequency model. Okay. Low frequency model you can see. So at low frequency capacitors are short. If you want to. At low frequency capacitors are open. Okay, fine. So yeah, so this is fine. So you can draw in a simple way like this. GMBPE and then RO. So this is at collector side, this is at base side, and this is an emitter. Emitter is already connected to ground, and other than that, this is collector where it's connected to RC, but this is VDD, which is now become AC ground, right? This is actually this was VDD, and this side it's R1 and R2, both are connected to, right? So now this is R5 and this is R, right? Okay. So what is the name of this configuration? It's not sourcely generated, by the way. What is the name of this configuration? No, no, this one, this circuit. This is pi model. Okay, fine. Common emitter. Okay. Now I'll ask you one more question before. Note that here I wrote it VTC1, but I can call this one as VCM1. If you are saying somewhere CM, it's common mode. Common mode is also, most of the cases, it's DC voltage. Okay. Also DC. So which configuration? This one is okay, common base. How many are agreeing with common base? Okay, then what about this one? What about this one? Right here. But are you guessing or you know the reason?
For these two, I don't know. But I.
So what is the reason for this one? Why it is common emitter? Actually, collector is also connected here to ground. If you look at this, it's also AC ground. Look at this. Hmm. You might be correct. I'm just asking you how you are finding out whether it's common emitter, common base, or common collector. So it's all depend on one fact that we are doing the AC analysis, right? And we have to look at the lowermost potential. AC potential which might be ground. That is what we are looking for, the lowermost available at. Let's assume that this is the configuration you are using. I need to find out which kind of configuration it is. So I need to look at the terminals and I have to see that which terminal has AC ground or the lowest potential among all. Or so here you can see that here I am applying sine wave, right? So this AC is already here. If I am applying here this kind of thing, at the output it's amplified and it's also AC. However, looking at this point or this point are relatively lower potential than these two, or everything has been compared with, like these two will be shorted by this, and this becomes AC, which is near to emitter, so that's why it's known as common emitter, right? Whereas in the case of this one, when you are doing such things, I am applying here voltage. So here it's AC, right? Here it's also AC. Yeah. What about this one? Zero potential in AC. So it's AC ground. So in that case, it has to be common collector because collector is AC ground. Whereas in the case of common base, you can see here when I did such kind of topology, here I give common mode voltage and calling it VCM1. Here in this case, this is sine, this is sine. What about this one? All DC will go to 0, right? In AC analysis, all DC will go to 0. So this is an AC ground, means this is common base, right? Can you draw the small signal model for this one? At low frequency, so there are no capacitors. Right? Is there anybody who wants like my TA or my help? Yeah, Gaurav, you got the answer? Where is Gaurav? Okay. So Yash and team, Yash Vashi, got the answer? Yes or no? No. Another yes is also here or no? Pinavia. Got the answer? Okay. Somebody wants to volunteer on stage? Vishal, you got the answer? Hmm? Can you try here so that like I can understand if you are making any mistake then I can help you. So it's very simple. Just one rule. Replace this three terminal device with the model which is known to us, right? And keep all the DC potential to ground, right? Because if you cannot do this one, like if you cannot draw a small signal model right now on paper, then like, afterwards I am not going to draw the small signal model. I am bypassing. However, it will be part of the exam also. Because this small question I will start to draw the small signal model. Okay, so okay, Vishal. So can you see this RC is connected to VDD? VDD is what? DC or AC? DC or AC? Huh? DC. So DC will go to 0 because you are doing. Yeah, you can keep this chair behind. So you can take that RC down to ground. So this was easy, no problem. Right? This is the emitter, this is collector, this is base, and at base, okay, so that is collector, this is connected to RC, and this is ground, this is connected to RB, and this is right, this is V out. Yeah, so connect it, connect RC. No, no, already your model was ready. So this is BJT. Now this happens. Like if you are standing on stage, you cannot think. This happens, right? No, I can understand. Like, when I was student and teacher asked me, then I cannot answer on stage. So there is one current source, Vishal. There is one current source, not the short circuit. In shunt with RO, there is one short line you made. So there will be current like this GMVP, whose value is GMVP. Look, this is the BJT which I am replacing. Okay. Yeah, that's correct. And now make RC with respect to ground. Is it difficult or? Okay. So now this RC goes to ground. Yes. RC from here, like RC. Okay. RB and yeah, RB. Take RB down. Keep one voltage source. Look, this is AC. You cannot make it 0. V in is not 0. And if there are multiple sine waves, like I'll send you, like I'll give another circuit afterwards. But okay, what about the base? Base is connected to common mode voltage. So what should I do? Look, R pi side, Vishal. R pi positive terminal is floating right now. So what you are supposed to connect there? VCM. Look at this circuit, VCM. Common mode is DC. So DC, what I am supposed to do here? Ground, because it's AC ground. You understand or not? Okay. So I'll call you again. Okay, don't worry. If you understood. Anyway. Okay, so let's try this one in that case. Okay. All the DC sources I am drawing with the red color. just for the information that they are DC, and you can make them ground. Okay. By the way, this configuration is cascode. I'll explain this maybe at the end of this chapter, but right now, let's make the small signal model. So you have to replace this three-terminal transistor with this particular two-port network. Right? Let's call this one as Q1, Q2. So let's call this one R51, GM1, VBE1, and this one is called RO1. Right? Draw the identical network, copy it, connect it at appropriate places. Right? So another, this Q2 has this small signal model. So this is base, like let's call it. So this is base B1, C1, E1, and this is also E2, B2, and this is C2. Right? So E2 and C1 has to be, so this is B1, C1, and E1. E1 is connected to RB, right? So I can keep here RB and ground. This part I can make it be in. This C1 and this, okay, this is E2 are shorted. Base 2 is connected to VCM1, which is actually AC ground. C2 is connected to V out, where there is one resistance whose name is RC. RC is connected to ground because of this VDD. Because of VDD, this becomes AC ground. Because of VCM1, this becomes AC ground. Is it okay? Can you draw this small signal model? Yeah. Now, no? Look, how many of them who does not understand this model? The connection of this one. Like Vishal didn't understand. You understand? You understand or no? So, okay. Okay, then in that case, I'll ask you maybe another circuit. Let's try this one. But we'll make. Uh, let's try this one. So Vishal, this one has to be replaced. Q1 has to be replaced with this one, right? Now this has. Now this is in your mind that this has to be there, but I'm going to name it like GM1, RO1, VBE1, and RPI1 because it's corresponding to Q1. Another one is also transistor, so I'm going to replace that with the same model, but names are different. This is RPI2, GM2, VBE2, and this side is RO2, right? Now here you can see that, let's name them. This is B1, this is E1, and this is C1. Let's call this one as B2, this one is E2, and this one is C2, right? Let's name them here also, like this is B1, this is, sorry, B2, E2, and C2. This one is B1, this one is C1, this one is E1. E1 is connected to ground, so I am connecting it to ground. No problem, right? Base 1 and collector 1 are shorted together, no problem. They are also shorted. Collector 1 and E2 are shorted, so they are shorted, no problem, right? Next to C1, there is RE, which is grounded. I kept it here. I'm taking output from E2 and C1 short, so let's call this one as V out. C2 is connected to VCC is DC, so what should I do? Ground. So let's ground it. And what about this one? It's connected to V in. Right? So this is small signal model. Right? Any doubt in this one? Drawing the small signal model. Super. Is it fast or with your mail? Okay. Anyway, so if you know that, then let's get back to the place where we were and let's talk about the MOSFET. Input impedance is infinite, or the impedance looking into gate is infinite, drain is R0, and source is 1 by 0, right? So there is a technique to find out the gain. So you have to look at in the path of source and in the drain, and you have to make the ratio of that which is going to give you the gain, right? So for this case, it's minus GM times RO, right? Minus GM times RO. Minus sign denotes because of the reason that the current is flowing in an opposite direction while doing the analysis of the Thevenin. So we kept minus over here, right? And the drain current and source currents are same. So the ratio of this one is going to give you small signal AC gain applicable only for low frequency. This is only applicable for low frequency. So it's like this. So with respect to frequency, it will be something like this. But we are somewhere here. Afterwards, we have to think what is going to happen here, 3 dB and other things, UGW. All these things will be the part of the next chapter, which is known as frequency response. Okay. So, if you understand this one, let's add few more things on top of. So now tell me, what is the small signal gain? If this is M1, this is RT, this is VDD. So what is the small signal AC gain? Yeah. So looking from here, right? This side is 1 by GM, no problem. What about here? This side is RO and this side is RD. So RD in shunt with RO, or you can say that it's minus GM times RD in shunt with RO. Same thing you can confirm with drawing the small signal model. Right? So you can apply always those Thevenin theorem and find out.
The RD is greater than
Of course, it will be always in kilo ohms. Have you ever connected RD or RC in ohms? No, right? If you are connecting RC in ohms, then there is problem. Then it cannot drive, and this becomes current as output. So sorry, voltage as output, right? Not current. So it is expected that RD will be there, which is actually uh, in the range of RO at least. Okay, so you can do the same thing like looking from source side, you are saying 1 by GM in shunt with RO in shunt with RD. So RO and RD are much bigger than GM. So that's why looking from here it's 1 by GM. Looking from here, gate to source voltage are 0, so this went to 0, so it's become RD in shunt with RO, right? Okay, so other than that, if this is the case where I am connecting this one to common mode voltage, then also source side what I am going to see, and from drain side what I am going to see. From source side, what is the impedance I am going to see? If this is common mode voltage, common mode is always DC by the way. 1 by GM, right? It does not make difference because gate is connected to ground. Earlier it was connected to VA, right? In this case, it's again RO because it also not make any difference whether it's connected to DC or AC, right? And in this case, if I'm looking from drain, okay, let's start from maybe source, might be easy. Looking from source, what is going to happen? 1 by GM. What about this one? 1 by GM. And what about this one? 1 by GM. This configuration is known as the diode connected configuration. This one is known as, by the way, this one is known as current configuration because you can control the current through the fixed DC potential. So this is known as current, this is known as diode, and one more was the resistive load, right? So we can make the few silver bullets that if NMOS or PMOS transistors with small signal AC gain will contribute impedance of minus 1 by GM at the source terminal, right? This is the case. Most of the time it's 1 by GM, no problem. Except one case, if it is source degeneration or maybe the cascade one. If you are looking at the drain side, it's RO, right? Now, if you connect that transistor in the diode configuration mode, from all sides it will be 1 by GM, right? And if you are making that one as current source, when we are saying the current source, the gate is connected to some DC potentials that contributes R0, right? This was the summary what we have studied on, right? Any doubt on this? So any doubt on this? Okay, if no doubt, then I'll ask you the question. Let's assume that this is a common mode voltage and this is start. This one is VD, this one is M2, this one is M1, and this one is V in, and this is ground. So can you tell me what is the small signal gain now? Note that the top one is PMOS. Okay, but all rules remain same. If it is diode connected configuration, looking from any terminal, it will be 1 by GM. Or you have to replace the small signal model of PMOS. Right? So if this is diode connected, then can you tell me what is the gain? The gain is minus GM1 into GM2 in parallel with, but this does not match the quantities, right? This is in mho and this is in ohms. Which one is 1 by GM? This is 1 by GM or? Okay, now fine. What about RO2? Okay, RO2 you neglected. Okay, RO2 is neglected because of. So here RO2 can also be neglected, and this will be minus GM1 divided by GM2, right? Now let's consider the situation where this is connected to VCM1. Now tell me the gain. So source side impedance is very easy, right? It's 1 by G, no problem. If you find any difficulty, please make the small signal model, then it's much more easier. Okay? No. You're not looking from, by the way, this terminal is source or drain? Drain. Now, you can again calculate the impedance. If you're looking from this side, it's 1 by G, no problem. If you're looking from here, it's again 1 by G. So what is the answer? Sakit? Yeah. Sakit? Yeah. So what is the answer? Rupansi? R1 is parallel to R2, okay. Okay, with minus sign, right? Yeah. Everybody agrees with this one, right? Yeah. But what if I connect here one resistance and make it source degeneration? Then looking from here, it becomes 1 by GM1 plus RS, not parallel, plus RS because it's in the same branch. So in that case, the gain becomes 1 by GM1 plus RS. So if you are going to see now the hook, still we are at the like if you are looking at the hook, now there is no problem about first three, right? Similarly, these three also. So notably, like looking from here is 1 by GM, but looking from top is something different. Okay? We have to calculate that. That's the next topic of discussion. And this one we have not talked till now. We'll talk that. But is there any doubt in this one till now? Any doubt? Okay. So that's all for today. That is.